Okay, so this is continuing P.4 on rational exponents. So rational means fractions. We're talking about exponents that are fractions. So on this one, if you say like 8 to the 2/3 power, so that 2/3 is actually an exponent there. So a is like your 8 right there, and m divided by n is your 2/3. So what you can do is that's rational exponent form. And then there's radical form. So radical form, you can convert it into one of two things. So the 8 goes here. That's like your A. N is down low. So the 3, the root, understand like the root or index of a radical is always right there in that spot. On a tree, the root is down low. The thing I wanted to mention there is the reason I drew that drawing is roots in a tree are down low, just like in this case, down low in the fraction, right? The 3 right here is the 3 goes right there. Whereas the exponents are up high in the tree. So here, the exponent is always elevated, on a problem. So 2 is the exponent. So you have a choice where you put that. So one place to put that is right there. You can put that as the exponent. Another place you can put it, if you want to. I really like this place of putting, so the 3 still goes there. So you can put the whole thing in parentheses and put the square on the outside, so the exponent on the outside. Either one are acceptable. And that actually makes a lot of sense. So something that would be very hard to do in our head, 8 to the 2/3. If you do it this way, it's really a two-step problem. That would be the cube root of 8, which is 2, 2 squared, which is 4. So that nicely simplifies just to be 4 there. So let's try one here. So what does that look like? So can you put this from radical form into exponential form? Right, so to do that, you're going to put it like, okay, 5 is like your A there, so 5 to the what power? And then you're debating, is it 2 over 3 or 3 over 2? Remember, the roots are always down low. The root is that index right there, so 3 is the root. Exponents are always up high, so 2 is the exponent. So 5 to the 2/3 is the same thing as the cube root of 5 squared. Go backwards. So in this one, we're going to go to radical form. So we'll draw the radical. There's a 7. Let's see, the root is 3, so I'm going to put that on the outside. And I have a choice where I put the 4. I could put the 4 here, or I could put the whole thing in parentheses, put the 4 on the outside. I kind of prefer that method, by the way. This one is going to be 8 to some fractional power. Uh-oh, what's the root? It doesn't say, but it's understood that it's a 2 there. So the root is 2, and the exponent would be 5. And then a really common one you might see is something like this. So 3 to the 1/3, that would be, if you put the radical there, so third root. So that's a third root there. And 1, you don't really have to write the 1. You could if you wanted to, but it's cube root. So 1/3 power is really cube root. Or if you see something like this, 4 to the 1/2, that's really the same thing as the second root of 4. In other words, 1/2 power is square root of whatever the number is. So 1/3 power is cube root, 1/2 power is square root. It's really handy to kind of know that. Try a couple problems here and simplify them. And these are actually surprisingly not too bad to simplify if you convert their form. So let's convert the form here. So this would be, let's see, 25. And that's the square root or second root if you want to put a 2 there. I'm going to put it this way. I'm going to put it to the power of 3. We'll put it on the outside. Again, I think it's a little easier if you do it that way. So this one simplified. The square root of 25 is 5. 5 cubed is 5 times 5 times 5, which is 125. It's not too bad, right? We were able to basically do that without a calculator in our head. This one, we're going to apply the rules we've learned. So this will be 27 to the 2/3 power, and 8 to the 2/3 power, because everything in there is being put to the 2/3 power. Now let's change the form. So this would be the, let's see, 27, the third root of 27, all to the power of 2, I guess. And the, let's see, put this in radical form. So again, the third root of 8, all to the power of 2. Simplify that, that would be cube root of 27 is 3. So there's 3 squared, or 9 on the numerator. And cube root of 8 is 2. 2 squared is 4. So 9/4. Didn't even need a calculator. We can handle it, right? Ooh, this gets a little tougher. So if you don't happen to know, like that one, it really helps to know. So like even on that one, maybe I went too fast there. So if you don't know the prime or the cube root of 27, for like when you get here, do the prime factorization of 27. If you're stuck, do the prime factorization. 3 and 9, 3 and 3. So the prime factorization of 27 is 3 to the third. So that's why the third root of 3 to the third is 3, right? That's why that simplifies just to be 3. Same thing with 8. If you don't know the prime factorization, do it. 2 and 2. So that's 2 to the third. So the third root of 2 to the third is 2. And then 2 squared is 4. So simplifying like that really helps. In fact, it really helps just to know the first few perfect squares, like perfect cubes. Like 1 cubed, 1. 2 cubed is 8. I have these memorized. 3 cubed is 27. I highly recommend it. 4 cubed is 64. That's a hard one to memorize, but you need it. And then 5 cubed is 125. I don't expect you to memorize perfect fifths. So this one, if you rewrite it, it would be let's see, the negative 32 would be the fifth root of negative 32 to the second power. So I'm going to do 32 prime factorization. Let's see what happens. 2 and 16, 2 and 8, 2 and 4. That's really 2 to the fifth power. So if I rewrite this, this would be the fifth root of negative 2 to the fifth power. So that would be the fifth root of negative 2 to the fifth power is negative 2, and negative 2 squared is 4. So we have an answer of 4 there. Let's try one more. Let me see, there might be, oh, there's a couple more. Okay, so cube root of 64. Again, it really helps if you know this, because that's going to make your life so much easier. If you know, oh, 4 cubed is 64, so this is just going to be negative 4. And by the way you know it's negative, you might think, well, oh, wait, we can't take the square root of negative. No, you can't take a square root of negative to get a real number. It'd be imaginary. Same thing with a fourth root or any even root, but odd roots of negatives are okay. Think about it. Negative 4 times negative 4 is positive 16 times another negative 4 is a negative 64. So you can have odd roots of negative numbers all day long without worrying about any kind of imaginary numbers. I want to show you one more thing that could happen on this. This will help you if you know this. So let's say we have something like this one may not even, well, let's simplify one. So let's try 1 over, I know, okay, so I'm making it up. That's why I'm struggling here. 1 over the fourth root of 81. So that's a 4. It's a really bad 4 right there. Okay, so to do this, let's just simplify the denominator. So that would be, well, let's do prime. Let's see, maybe you don't know the prime factorization of that. So 27, 3 and 9, 3 and 3. So that's really 3 to the fourth. Oh, that's helpful. So this is really 1 over the fourth root of 3 to the fourth. You could write this, so that's really 1 over 3 to the, if you wrote it in fractional exponent for the fourth root of 4. There's a different way of thinking about it, right? So that's 1 over 3 to the first, essentially, when you simplify. You might have seen that, right? When you saw it like this right here, you might just, oh, that's just 3. That's fine. I just wanted to show you a different way of thinking about it. The other thing, sometimes they'll say, put this into rational exponent form, like a to the m divided by n. Well, this is not quite rational exponent form, but you could easily switch it to that, because how can you make this guy migrate up to the numerator? Well, what kind of exponent would make it migrate up to the numerator? A negative exponent. So you could say that's 3 to the negative 1 if the goal was to put it into this kind of form, like rational exponent form. Good. I have one more thing to show you. This is some really challenging problems here, some of them. So let's see, let's try these. Okay, so this one, I think we've done this with radicals before. So like you're looking for groups of three, right? So this one would be a two comes out, but underneath the cube root, there's still one two left over because there were four of them. The x's, one x comes out because a group of three becomes an x, and then x squared would be left over inside. So I kind of left too much room there, but that's the answer would be simplified to that. Same problem written in rational exponent form. So anytime this guy is improper, it can be simplified. So the way to simplify this is first to write this as a mixed number. Usually I don't like doing this, but 2 to the 1 and a third power, x to the 1 and 2/3 power as mixed numbers. And so now you can say, well, the 2 to the first is just 2. 2 to the 1/3, I'll write separately. And then times x to the first is just x, that's like 2x. And then I'll write the x separately, so x to the 2/3 separately. So that could be written, that could be the answer, which is really the same thing as this answer right here. It's just written, it's simplified in rational exponent form. Let's try this one here, and then we'll try some of these down here. So let's try this one. So this one, if you just start simplifying it, it would be, it looks like it's 3 in the numerator. That first numerator would be 3 squared or 9. And then this would be x to the 4/3. And the denominator, that's also being squared. So 1/2 times 2 is 1, so that'd just be y times, I guess, y squared. And this one would be x to the 2/3. So that's going to go up to the numerator and be x to the 2/3 in the numerator. So now if some of the stuff cancels, like this y cancels nicely with, there's two y's up there, now there's only one. Kind of handy. And then we add exponents here, so this would be 9, and then x to the 4/3 plus x to the 2/3. So 4/3 plus 2/3 is 6/3, which is 2, so that'd be x squared and y. So that simplifies to be just that. Now, when you come to a problem like this, I don't know how to do this in radicals. So really tough problem, convert them to rational exponents. So this is what this means. So we're going to have x to the 1/2 times x to the 1/3. Right? Well, now I can do this one because the rule is with exponents, you just add. So now I have to do x to the whatever 1/2 plus 1/3 is. 1/2 plus 1/3. Let's just kind of do a little conversion there. So if I multiply this one by 3/3, multiply this one by 2/2, I get, let's see, there would be 3, 6 plus 2, 6 is a total of 5, 6. And this one looks really intense here. Again, I'm going to try to simplify this to rational exponent form and see what happens. So let me deal with this inside part first. So if I deal with that, that'd be square root of x times, I guess that would be x to the 1/2 power. And now all of that is being square rooted, right? So even that x to the 1/2 power is being square rooted. So I'm going to write it like this. So I'm going to say all of that, as in x times x to the 1/2 power, is being square rooted. It's all being put to the 1/2 power. There's a lot of different ways to deal with this. Some people will kind of distribute this, like simplify that inside of there. I think that's not a bad plan. So if you did that, x to the first times x to the 1/2, you add the exponents to be x to the 1/2 power, or in other words, x to the 3/2 power, to the power of 1/2 that's still out there. Power, you multiply, so this would be equal to x to the 3/4 power. Wow, so we simplified it. That guy is equal to x to the 3/4 power, which is kind of neat, actually. Pretty tough little problem. Okay, that's your extra lesson for this P.4.